am Connor, and I'm going to be talking about my project into forest biomass supply to provide energy for a large-scale industry in Canterbury, New Zealand. Sorry, camera.
It always takes just a second to add this profile to each button.
There we go. So there's quite a pressure on industries to reduce their carbon footprint. One way of doing this is to switch to a more sustainable energy source, like going from coal to biomass. The dairy sector alone uses 20% of New Zealand's coal use. If Fonterra and Canterbury were to switch over, their 3 processing facilities in Canterbury would need about 500,000 metres cubed of biomass per year. So is there a way to achieve this sustainably? There's 3 sources of biofuel. So you've got your residues from the mill and forest. And these are created as a byproduct of your normal operations, as well as purpose-grown forests supplying biomass purposefully. Internationally, this is done. So they do a lot of it on short rotation crops, mainly willow and poplar. A lot of it's done out of China and parts of Europe. And this is done on good quality land with intensive land management strategies. In New Zealand, the research is a wee bit thinner. Simon did a interesting research article in 2024 looking at it and came out with radiata pine and eucalyptus being best suited for short rotation energy crops in New Zealand. Radiata being highlighted for its low risk and high area to be planted, as well as entrance into the ETS for those early carbon credits. Do we have enough wood in Canterbury to supply that amount of biofuel to this industry? From the Canterbury Wood Availability Report, it looked at 3 different scenarios. That one there is the split non-declining yield, which was the most likely out of the 3. And as you can see, we are going into a bit of a lull in the wood supply. It's a bit hard to see on the projected, but it's around about there is the maximum of the pulp logs for future, as it decreases over the next few years, but increases in 2040. But that is still shy of the 500,000 that is required for the biomass. So I'm investigating into 3 different forestry regimes set out to supply biofuel for a large coal user. These 3 regimes are a short rotation forest, where at age 17 we cut everything down and send it off to be biofuel. A dual purpose, where we let that forest mature to age 30, then separate the saw logs from the biomass, and then a transitional forest where we start off at age 17, providing the volume of biomass and then transition into that full rotation to get the profits from the saw logs. How I did this was I got the yield tables from the National Exotic Forest Description, as well as the Canterbury ETS lookup tables and costs associated with all the regimes. I adjusted that with the PPI to account for the inflation of the costs found on the different years through the literature. I then modelled the planting regimes for each of the 3 forests. Then did an economic analysis on the NPV, LEV, and break-even delivered wood price for each of the 3 regimes, and did a sensitivity analysis on those key variables. In regime 1, I found that the land needed was about 43,500 hectares in total, with yearly planting of just over 2,400 hectares each year over that 17 years. The economic analysis was pretty bad. It came out to negative 5,500 and an LEV of 2,273, which is quite low compared to the $7,000 original land price. The break-even price of the biomass came out to about $148 per metre cubed, and at that point you're better off just going and buying the higher quality logs anyway. The full rotation forest The economic analysis did improve. It is still negative. The NPV is still negative. The LEV improved up to 3,000, just under 3,700, but that's still quite negative, quite lower than that $7,000 original assumed price. The break-even price of the biomass increased quite a lot by up to 326, but that's because once the price of the biomass goes past the price of the sawlog, it has to compensate for that lower sawlog price to help bring it back up to a positive NPV. The transitional forest, the planting regime was a wee bit different. So it started off the first from 0 to 4 years of planting is you're just planting that 17-year rotation. Then from 5 to 17, there's an additional planting for full rotation while still doing that 2,400 planting for the short rotation. In 18 to 30, the 30 rotation starts. So you've got the 19 to 66 plus an additional short rotation. Now those additional plantings help bring the transitional period. So you can still supply that 500,000 when you're transitioning from that 17-year to a 30-year rotation. The sensitivity analysis kind of came out to what you'd expect. When revenues go up, the NPV goes up, and when costs go up, the NPV goes down. That was linear with a wee bit of a curve, because of the discount rate applied to those later revenues. But yeah, pretty much what you would expect. So my key findings were that there is quite significant trade-offs between supplying that biomass early on and waiting for the full rotation to get those higher profits. The sensitivity analysis showed that the project was most sensitive to the carbon prices as well as harvesting costs, and the overall viability was that it's not viable. It's not profitable enough under those base assumptions. Future research that could be looked at would be optimizing the species and silvicultural regimes as well as harvesting systems specific for biomass, kind of like what you get over in Europe and parts of China. These are some of the key references that I've used. Is there any questions?